welcome everyone. This is the first lecture of the course called Hydraulic Engineering, and I'll start with fluid properties. My name is Mohammad Saud Afzal. I'm a faculty at Department of Civil Engineering in IIT Kharagpur. So to start, one of the most basic things that we need to know about the properties are the dimensions and units. As you have already read before in your class 10th and 12th, the dimensions of each term on the two sides of an equation have to be the same. That is the most important requirement for the dimensional analysis. Some of the common dimensions of mechanics are length, which is denoted by L, time, which is denoted by time, mass, which is denoted by m. These are the three basic dimensions that we generally consider. Force is given by mass into acceleration, and in terms of dimensions it can be written as mlt minus 2, because mass is m and acceleration is rate of change of velocity, which gives lt minus 2. Temperature is denoted by theta. So some of the important quantities, symbols and their dimensions are given. Velocity is given by v, its dimensions are Lt to the power minus 1. Acceleration, similarly as we see in the last slide, is Lt minus 2. Area is given by L square. Volume is length cube. That discharge is L cube T minus 1. Pressure is mL minus 1 T minus 2, and gravity is LT minus 2. So you should be able to show some of these properties by doing this analysis, by writing the basic equations. For example, what you can do is, for example, pressure is given by force divided by area. So you can write down the dimensions of force. You can break up force into mass into acceleration divided by area. So mass basic dimensions you know, acceleration you know, and area also you know. So for example, pressure comes out to be ml minus 1 T minus 2. So density is given by rho, its dimension is ml minus 3. Specific weight is given as gamma. We will come to that, what specific weight is. Dynamic viscosity is the dimension. These are some of the more complex quantities for which we have simply written down the dimensions, but you can actually derive it. We will see. Kinematic viscosity nu is given as L square T minus 1. Surface tension sigma is mt minus 2. Bulk modulus of elasticity E is given as ml minus 1 T minus 2. So these are actually fluid properties. These are some of the most important ones. As I was telling you, I am going to tell what specific weight is. So specific weight can be related to the density by this equation. Specific weight is rho into g. And similarly, we can relate kinematic viscosity and dynamic viscosity through density again. So n here is nu, m is dynamic viscosity, m as can be seen in the slide. So nu is mu by rho. And now as you can see, since we can relate density and specific weight through rho, and we can also relate dynamic viscosity and kinematic viscosity through rho. So there are how many independent properties? One, surface tension, second is bulk modulus of elasticity, one of the viscosities, and you can either choose density and specific. So that means there are only 4 independent properties presented in this slide. What is the definition of a fluid? According to Young, Munson and Okishi in their book, a fluid such as water or air deforms continuously when acted on by shearing stresses of any magnitude. One of the important word here to note is deforms continuously. So that is what a fluid is. So I have a question, why isn't steel a fluid? because the steel does not deform continuously if a small force is applied, and by definition if you apply whatever single force, simple most force, the fluid will deform. Now going to some of the density and specific weight, just to give you a brief revision from before. Density is defined as mass per unit volume, rho. So this is called specific mass. Density of water is 1000 kilogram per meter cube. Density of air at atmospheric pressure and 15 degrees centigrade is given by this curve. This is a function of the temperature. This figure right now shows the variation of the density of air varying from 0 to 100. In this figure now, it's to a zoomed image. So what happens mostly between 0 and 20? The reason of doing this is the temperature that we encounter mostly 0 to 20 degrees in nature, especially in this part of India. It goes up to 30-35 as well, but this gives a zoomed image so that you are able to see in detail how the pressure variation is. A specific weight of water, that is called gamma, is given is 1.22 kilogram per meter cube for air, and density and specific weight of water is rho g, 9806 Newton per meter cube. So proceeding to our next topic of the fluid properties, it's important to note that we define fluid as the something that deforms. So we will see an example where fluid deformation between parallel plates is done. So this is the side view where a force F is applied and the upper plate starts moving with velocity u, and the thickness of the total thickness is given here, denoted as T. So as I told you, force F causes the top plate to have velocity u. Now what other parameters can control how much force is required to get a desired velocity? As has been seen from the experiment, distance between the plates, which is denoted as T, is quite an important parameter. Area of the plate A is also very important parameter. Viscosity mu is also important parameter. But what happens if these parameter increases, and what does F do? So F is found out to be directly proportional to mu, area, speed, but inversely proportional to the distance between the plates. So these arrows indicate on the left side that the parameters or the F increases, on the right hand side denotes this decreases. So for F to increase, as you can see on the left hand side, the distance between the plates should go down, or if the distance between the plates go down, the force will increase, or if we increase the area of the plate, the force goes up, and if the viscosity of the fluid increases, then the force increases. Shear stress. So force, as we have seen in the last slide, is given as mu times A multiplied by u divided by the distance between the plate T. So mu can be written as Ft by Au. The dimensions of mu is Newton second per meter square. I think you should do this derivation after this lecture is finished at your own convenient time. Shear stress now is actually defined as force by area, and this is this tangential force per unit area, and its dimension is Newton per meter square, or units is Newton per meter square. Shear stress therefore can be written as mu u by t. What is u by t? U is the velocity, t is the distance between the plates, or we can also call it as rate of angular deformation. So the units of this is 1 by seconds. Tau therefore can be written as mu du by dy. As we have already said, it is rate of angular deformation. What is du by dy? It's change in velocity with respect to the distance, as in terms of differential equation. So shear stress is our general equation that relates shear and viscosity, and this du by dy is also called rate of shear. Okay, coming to fluid viscosity. Some examples of highly viscous fluids are molasses, tar, if you have more concentration of oil, or glycerine. These are some of the things which are highly viscous. So, what is the fundamental mechanism of viscosity in gases? It is due to the transfer of the molecular momentum. In case of gases, the viscosity increases as temperature increases. Also, the viscosity increases as the pressure also increases. Liquids, it happens due to cohesion and momentum transfer, and here the viscosity decreases as temperature increases. It is very important to note that it is quite different from the gases, where the viscosity increases on increasing the temperature. Also, the viscosity in the liquid is relatively independent of pressure, for example incompressible fluid. Now, one of the examples that we will talk about is used to measure the viscosity of the water. It is a very standard experiment. So, the inner cylinder, in this particular case I have broken it down in form of a numerical as well. So, the inner cylinder here is 10 centimeters in diameter. There is another outer cylinder as well. So, the inner cylinder being 10 centimeter in diameter, and it rotates at 10 rotations per minute. The fluid layer in between those cylinders is 2 millimeters thick, and the height at which it is 20 centimeter high. If it is given that the power required to turn the inner cylinder is 100 into 10 to the power minus 6 watt, what is the dynamic viscosity of the fluid? So, as you have seen, one of the equations that can be used to find out the dynamic viscosity is tau is equal to mu du by dy, and F is equal to mu au by T. These are the same equation. One is written in the differential form, other in the form which we normally write, we require in this case as well. So, for to be able to solve this, I have written all the quantities that I know. Radius 5 centimeters of the inner cylinder, thickness 2 millimeter fluid, height is 20 centimeters, power is 110 to the power minus 6 watt, and omega is 10 rotations per minute. So, F is given as mu a u by T. We need to know what u is. U in this case will be r omega, or omega into r. So, what actually is omega? Omega is 10 revolutions per minute into 2 pi radians by revolution into minute by 60 second. If you do this calculation, it will come out to be 1.047 radians per second. Omega can be directly obtained from this RPM value. Now, we also need to find out what an area is. Area is 2 pi r h. So, it will act across all the surface of the cylinder, and we know the value of r, we know the value of h. So, F is written as mu, A is written as 2 pi r h, and u is written as r omega, T is as it is. So, if we break it down this equation in terms of omega and r, this is what we get. F is equal to mu multiplied by 2 pi multiplied by omega multiplied by r square h divided by T. The power is F into V, force into velocity, or F omega r in our case. So, power can be written using the equations of F and P given above as mu 2 pi omega square r cube h by T, and using this equation, if you take T on the other side and 2 pi omega square r cube h down, you can obtain mu as power into thickness divided by 2 pi omega square r cube h, and on substituting the values, P as 100 into 10 to the power minus 6 watt, thickness as 2 millimeters, Omega we already found out, it was 1.047, and r cube, r is 5 centimeters or 0.05 meters, and h is 0.2 meters. We can get 1.16 into 10 to the power minus 3 Newton second per meter square. So this is one of the standard ways of finding the viscosity of water or any fluid for that purpose, and that also demonstrate one of the examples in real life how are you going to solve for the value of the viscosity. Now what is the role of viscosity in statics? It is important to note that fluid at rest have no relative motion between layers of the fluid, right. So statics means rest. So when the liquids do not move, there will be no velocity difference between those two fluids, so du by dy is 0. Therefore the shear stress is 0 in case of fluid statics and is independent of the fluid viscosity. In case of dynamic, fluid viscosity is very important because the water moves, different layers will have different velocity, and thus will be the velocity gradient du by dy. So now, as we briefly touched dynamic and kinematic viscosity, kinematic viscosity, also called nu, is a fluid property obtained by dividing dynamic viscosity mu by fluid density. So mu and nu are related by fluid density as given below. Nu is mu by rho, and if we write it in terms of unit, we get nu as meter square per second, as we have seen in the slides at the beginning of this lecture. This also has a connection to Reynolds number. Reynolds number is a concept that we will study some weeks from now, but I think this is a fluid mechanics and hydraulics class, so it is important to introduce the value. Reynolds number is given by rho Vd by mu, and since, as we can see from the above, that mu can be written as rho into nu, we can simply write Reynolds number as V d by nu. V is the velocity, d is characteristic dimension, or in case of a particle of a sphere, it could be a diameter, and nu is the kinematic viscosity of water. So we are actually going to solve couple of problems now, where you will see how to be able to solve for the shear stress at under different conditions. So the question says the velocity distribution in a viscous flow over a plate is given by u is equal to 4y minus y square for y which is less than 2 meters. Here u is velocity in meters per second at a point distance y from the plate. If the coefficient of dynamic viscosity is 1.5 Pascal second, determine the shear stress at y is equal to 0 and at y is equal to 2 meters. Okay, so how are we going to solve this? We will, so what is given is u is equal to 4y minus y square, right. So therefore the first step is always finding du by dy for finding shear stress. This is very important. So using this equation here, if you do du by dy, so going to the basic differential mathematics, 4y will become as, so d dy 4y minus y square will be d dy. I am going very slow for this one because I am not sure if it is too obvious for you. So this can be written as 4 because this d dy of 4y, 4 is a constant, so this will turn out to be 4, and d dy of 2y square, 2 will come out, so it will be 2y. Okay. Then we also know that shear stress tau is equal to mu du by dy. We have already found out du by dy, and we already know what mu is, right? So at y is equal to 0, so at 0 what I do is I indicate shear stress at 0 as t tau 0. It will be given as so this will du by dy will be 4, because 4 minus 2 into 0 multiplied by dynamic viscosity, which was 1.5. So this comes out to be 6.0 Pascal second. In other case, at y is equal to 2 meters, if you do here 4 minus 2 into 2, that comes to be 0. Therefore tau at 2 will be mu 4 minus 4, that is 0. So this is the first question that is there. So now we can go and see. So this problem we were able to solve. Now there is another problem related to this, the first part, and that also we are going to solve. So what it says is a 90 Newton rectangular solid block slides down a 30-degree inclined plane. The plane is lubricated by a 30 millimeter thick film of oil of relative density 0.9 and viscosity 8.0 poise. If the contact area is 0.3 meters square, estimate the terminal velocity of the block. Here also, as you can observe here, the most important part here is the viscosity. Because of this viscosity, there is going to be friction or shear stress, and then the block will have some friction, and therefore because it will counter the weight of the gravity, and which is generally taking the block down. And then now let's actually start how to solve this problem. So we are going to the white screen again. So as last time, it's important to always write down what are the things that are given. So we are given that the weight of the block is 90 Newton. One of the other things that we can actually do is we can try to have a rough diagram. This is theta and this is the block. Suppose this is moving with velocity v, a terminal velocity which has been achieved. So when it is moving down under the influence of the weight, there is a shear stress that is opposing the motion of the block, and the weight will be acting W downwards. So as you would recall, you used to have something called free body diagram in your mechanics. This is very similar, just to make the block. So weight is given. Let's assume v is the terminal velocity, which is the value that is asked in the question, and theta is given as 30 degrees. So this theta is actually 30 degrees. So important to note that at the terminal velocity the sum of the forces acting on the block in the direction of its motion is 0. So what happens at the phenomenon called terminal velocity? If there is the net force acting on the block is 0, then only there will be a terminal velocity. Otherwise, the block will accelerate or deaccelerate depending upon in which direction the force is larger. So if we write down the force balance equation, so we can see the weight is acting downwards, right? So there will be a component of the weight acting in favor of the motion, and that component is written as W sin theta. And what is opposing the motion is the shear stress tau, right? So the force due to this shear stress is given by tau into A, and that should be equal to 0 in case of terminal velocity. Here tau is shear stress on the block, area is the area in contact area or the area of the block, because the whole area is in the contact, and tau is mu du by dy, or mu if the terminal velocity is v and y is the thickness h, because that is the area that is in contact. So h is thickness of oil film. Mu is given as 8 poise, or in terms of Pascal second. So resuming, mu is 8 poise and in terms of Pascal second is 0.8 Pascal second. Simple conversion. H is given in the question as 3 millimeters or 3 into 10 to the power minus 3 meters. This is quite important to note down, because now I have a new screen. So what I am going to write down are some of the important equations that we have seen in the previous white screen. So one of the equations was W sin theta minus dA is equal to 0, and tau is equal to mu du by dy is equal to mu v by h. Okay, here area is given as 0.3 meter square. Now if we substitute the various values in above equations, so W is 90 Newton, it is given, sin 30 minus shear stress is mu, that is 0.8, V divided by H is given as 0.3 into 10 to the power minus 3 multiplied by area, that is 0.3 is equal to 0. So what we get, So bring this side, V is 90 multiplied by 0.3 into 10 to the power minus 3 divided by 0.8 multiplied by 0.3, or this becomes 45 by 80. So this will be 0.5625 meters per second. We can verify this equation, the calculation, but 90 sine 30 will be 45, and if you do 0.8 into 0.3 and divide by 0.3 into 10 to the power minus 3, this will give you the value of 80. So how this has been done? So this 45 comes from here, and using these two, this comes here. So I know it's you can get confused, that's why I'm trying to point it. So this gives us the terminal velocity 0.5625 meters per second. Great. So now we can proceed. So these were the two problems that we decided to solve for this particular lecture. Now the next topic is going to be the fluid properties, and this we will take up in the next class. Thank you.